Hey everyone, my name's Martin, and in this video we're going to explore Docker, one of the most powerful tools for developers and system administrators today. If you've ever wondered how to easily package, ship, and run your applications anywhere, Docker is the answer. So let's dive in and see how containers are changing the way we build and deploy software. First off, we're going to dive deep into how containers actually work under the hood. You'll see exactly why they're so incredibly lightweight, portable, and blazing fast to start compared to traditional solutions that have been around for years. We'll break down the key components and show you what happens when you run just a single command. Then we'll shift gears and explore how virtual machines operate, going through their complete boot process step by step, from hypervisor all the way to your running application. This side by side comparison will make the fundamental differences crystal clear, so there's no confusion about when to use each approach. By the end of this section, you'll not only understand the technical magic behind both technologies, but you'll also know exactly why containers have revolutionized modern development workflows. Inside a virtual machine, the boot process looks very similar to a normal physical computer. It's a full startup sequence that takes time and resources. First, the VM firmware such as EFI starts up and finds the bootloader on the virtual disk. The bootloader then loads the operating system kernel into memory, along with an initial RAM disk that contains the minimal tools and drivers needed to access the real disk. Once the kernel and the RAM disk are loaded, the system starts the init process, which on modern Linux systems is usually systemed. From there, system launches all the required services like networking, logging, and security features. And finally, your application starts running on top of the fully initialized operating system. This entire chain explains why VMs can take tens of seconds or even minutes to boot, consuming gigabytes of RAM and disk space along the way. Now let's switch over to containers. Here on your screen, you can see just a few processes running smoothly. The key insight is that containers are essentially nothing more than regular processes within the operating system itself, cleverly isolated from each other. Unlike virtual machines, they don't require a full OS boot or hypervisor overhead. Instead, they simply leverage the host kernel directly to run your app securely and super efficiently. That's why they start in milliseconds and use way fewer resources. Now let's jump into the host system and open up the command line. First thing we'll do is list all the running processes right here. Just type PS and hit enter. You'll see everything that's currently active on this machine, giving us a clear view before we dive deeper into how containers fit into this picture. Now let's fire up a Docker container with Nginx. It's super simple. Just run this command: docker run -d -p 8080:80 nginx. This pulls the official nginx image, if you don't have it, starts the container in detached mode, and maps port 8080 on your host to port 80 inside the container. Boom, your web server is live in seconds. Now let's list the running processes again. There it is. Nginx is up and running on the host operating system along with all its worker processes. What you're seeing here is purely the host's perspective, not a peek inside the container itself. This proves that the container's Nginx is just leveraging the host kernel directly without any separate OS overhead. Now let's take a look inside the container itself. Just run docker exec to jump right in and check the processes. As you can see, the exact same Nginx processes are running here too, but they have completely different PIDs, like PID 1 for the main Nginx process instead of what we saw on the host. This magic happens because of PID namespaces, one of Docker's core isolation features that creates a completely separate process ID space for every container. From inside, it feels like PID1 is the very first process on a brand new system, even though it's just a regular process on the host. This namespace trick is what makes containers so secure and self-contained without needing a full virtual machine. When we zoom out and look at the bigger picture, we have the initial PID namespace. That's the host's main process space where everything starts with PID1 as systemed. Then each container gets its own child PID namespace, a completely isolated view nested underneath. Inside its own namespace, the container's Nginx becomes PID1, while on the host, it's just another numbered process. This hierarchy is what makes container isolation so elegant and efficient. What becomes PID1 inside the container is something we explicitly define in the Docker file using the CMD or entry point instructions. These set the main process that kicks off when the container starts. Now let's list all the namespaces available in our Linux system. Here are the main ones Docker uses: PID namespace, mount namespace, network namespace, UTS namespace, IPC namespace, user namespace, and cgroup namespace hides and limits resource controls.